Start recording. All right. Thank you so much, everybody, for coming, and thank you for our two fabulous speakers. This is going to be great. I'm super excited about the talk tonight, and I'm going to do a quick introduction. So, I know Professor Afshordi from Iran from when we were both undergraduates at physics department in Sharif University, but then at some point our paths got diverged. He became an astrophysicist, and I went to experimental physics in soft condensed matter. But now this is a great time. I'm so happy that he can come back and give a talk to us. So Professor Afshordi is a professor at Department of Physics and Astronomy at the University of Waterloo, and he's an associate faculty at the Perimeter Institute for Theoretical Physics in Ontario, Canada. His prize-winning research focuses on competing models for the early universe, dark energy, dark matter, black holes, holography, and gravitational waves. He has contributed to Scientific American and was a consultant to PBS Nova, which we love. And his work has been featured in numerous popular media outlets, such as Scientific American and Science, as well as in The Guardian and in New York Times. Professor Phil Halper is a fellow in Royal Astronomical Society and a science popularizer. Sorry, I'm rushing through my reading. He's the creator of popular YouTube series Before the Big Bang, which has had several million views, and was previously a journalist in residence in the Penn State Institute for Gravitational and Cosmos. His astronomy images have been featured in major media outlets, including the Washington Post, the BBC, and the Guardian. And he has published several papers in peer-reviewed journals, and he lives in London. Are you in London right now? It must be very late.
Yes, I am. Yeah, yeah.
Oh,
Yeah.
okay, great. We doubly appreciate you coming here and giving a talk. Yeah, so let me make you guys co-host of this meeting, and you guys can take it away. So Niyayesh, you are the co-host right now,
Mhm. Yes.
and Phil, you're a co-host right now. Okay, take it away. Yeah, we're excited.
Cool. Yeah. Let's see. Okay, we'll see whether I can get this to work. So I guess you see the screen or no?
Yes, we
Your
can.
screen share-
Hmm.
You can see the screen. Okay.
Yes,
It says your screen sharing is paused, but you guys can see it. Okay.
yes.
Um, Very good. I'm excited to talk to everyone here. I see lots of kids that are very excited. I'm also very excited. I guess we are all excitement is very infectious. Um, and yeah, this is actually early for Phil. I work we work for a long time, and yeah, he's an amateur astronomer. Astronomers go to bed late at night, or don't go to bed at night. Go to bed in the morning. So this is I think this is a good time for Phil. Um, and yeah, so this is not your typical, I guess, scientist duo. We have very different paths. I come from Iran, as my friend Azadeh mentioned. Phil is from London. Phil has a more exciting, interesting resume than I, but I just want, I'm not going to say too much because I think Azadeh already introduced Phil. I'm just going to say that when I ask my son, so I have a 9-year-old and a 13-year-old, my when I ask my 9-year-old what he wants to be, he doesn't say he wants to be a scientist. He says he wants to be a YouTuber, and Phil is already a YouTuber, so he's yeah, he's already my son's role model, you could say. Yeah. And yeah, we met about 5, 6 years ago when he visited us in Canada. Right. So I think yeah, and we hit it off and worked on different projects. So the biggest one is the one I'm going to tell you about, which is called it's had a different name originally, but now it's called the Battle of the Big Bang. Um, and I'm going to tell you a little bit about the Big Bang, some of it about the stuff that we worked on together, but just I'm going to introduce you to the ideas that we are so fascinated about. And This is, I guess, actually I have now the picture of me and Phil. We haven't gotten together too many times, I think a handful of times, but this is one, I think maybe the second or third time we met. We haven't exactly,
I think your screen is, are you showing a picture of you and Phil?
yeah, you don't see it?
Yeah, no, we don't see it. So
Oh,
let's
I see, okay. Um,
maybe share again.
I
And
stopped sharing. Okay, I'm
mhm.
gonna stop sharing. And yes. Okay.
Let's
Yeah,
see.
okay, I'm just gonna share my desktop now.
Okay, now we can
As
see it. Yeah, it moves now. So
everything.
hopefully.
Okay, good. And yes, so
Okay.
this is
Yeah, it's
uh,
going forward. Yeah, great.
okay, going forward.
Mhm.
Sorry, I need to give. I saw someone's hand raised. I guess it was just about this, right? I think someone's hand was raised. Okay. My son needs more screen time in Nintendo. I don't know how many of you sympathize with that. Okay, very good. Um, okay, so I think Kai, some people are raising their hands. Azar, you're on top of this, I
Yeah,
guess.
I think,
Okay.
yeah, just go ahead and give your
Okay.
talk, start your talk, and then we call on them. Yeah, go ahead.
Okay, very good. So we haven't exactly coordinated like back and forth about what part I'm going to say and what part Phil going to say, but I think we can feel free to jump in at any point.
Well,
Uh,
Niyayesh, why don't you give your talk, and then I'm going to go over some of the animated
Okay, very
films
good.
that we've made about the different ideas for what
Okay,
triggered the
very good.
Big Bang.
So I'm gonna use some of your videos that you sent me, but then you could talk more about them as well. And
Okay.
yeah, but again, let me know at any time. Okay, so what's the Big Bang? So imagine everything, as stars, planets, you packed into a hot, dense primordial soup. So when primordial means something that existed long ago. Um, so let me move these things around. And then boom, expansion begins. So everything starts expanding, moving apart from each other. That's the picture. One of those movies I was telling you. It's how universe would start, or something like that, and gets cooler. And there are sound waves and fluctuations, waves going around, and slowly, when it cools, gravity brings things together and makes galaxies, stars, and eventually planets and life. And what you see, and this is a simulation of how universe began, you see it actually goes up to a few billion years after the Big Bang. That's where the simulation stops. But this is roughly the picture that we have. Universe is, boom, explodes, expands, gets colder, starts hot, gets colder, and as it gets colder, gravity takes over and then get things close to each other, and from that you form galaxies and stars and so on.
So I should just say
Yes,
it, Nash. Those
yes.
bright patches there are galaxies. So we
Okay,
start
good.
with this hot primordial soup.
Mm-hmm.
Interestingly, I was just reading a Chinese creation story, and
Mm-hmm.
I didn't know this when we wrote the book. So this is not in the book, but
Yeah.
they said that the universe was opaque. It was first off, it was a great emptiness. Then there was energy. Then it was opaque, so you couldn't see through it, and that's pretty accurate. So then what you're seeing here are galaxies. All those bright patches are galaxies, and
Mm-hmm.
clusters of galaxies forming gradually as gas collapses in on itself, and it forms in these filaments that you see there.
Okay.
That's right.
Looks like Kai has a question and Nora's hand was up. Kai, you go ahead, and then Nora, Felix, and August, they have questions.
What
Kai,
is T? I see T in the top right corner.
Good.
What's that variable?
Yeah, so that says time after the Big Bang. So G is a giga, like when you say gigabytes, for example. Giga means like a billion. So means a billion years. So this is 2.7 billion years after the Big Bang, which means 2 billion years and 700 million years after the Big Bang. So that's what the T is, right?
Okay.
Felix, was that you? Sorry, that was Felix, right? Felix, did you ask your question?
No.
Felix, go ahead.
My question was, when did the first atoms form?
Good question.
Good Good, great question. And I'm gonna come to that in a little bit, but short answer is 400, about around 400 million years after the big, sorry, around 400,000. 400,000 years. Thank you for correcting. 400,000 years after the Big Bang. Very good. Thanks. Thanks for
Okay.
August. Yeah, we're gonna cover that apparently. August, go ahead.
So like it was just a bunch of stuff and then like it turned into like so it lived in like hydrogen atoms and then like
Yeah.
heavier atom and then like heavier and heavier atoms.
Yeah, that's true. You get heavier atoms later on. So the heavier atoms, they actually form so they get hydrogen and helium are the first atoms that you form. But then much later on when you form stars, the biggest stars could actually make heavier atoms like lithium, sodium, iron, all those things. They actually come from much bigger stars.
It's been some of those elements come from exploding stars, and it's been
Right.
said that the stars died so that we can live.
Oh, interesting. That's really good.
Right.
Yeah, Kai, you've been waiting patiently. Kai, you go ahead, and then Dash, and then we can move on.
The first material, the first sound of material was actually subatomic particles, which turned out to be the subatomic particles of lithium and beryllium, which turned into elements.
That's a very good point. Yes, that those are the first elements indeed. Yes, lithium and beryllium and hydrogen and helium. That's right. Those were actually the ones that were made in the Big Bang. Good
Awesome.
point.
Very good.
Good.
Dash, do you have a quick question? And then we move on after this, okay? Dash, go ahead.
Okay.
Ask this section.
So, when matter actually first came into existence, you can't say that it happened at any time because at that point, time didn't even yet exist.
Great question. We're gonna get to it. Okay, we're gonna get to what time and space and when time came to be. I
All
know
right.
that's a
So
good question. Very
awesome.
good.
So let's just let the speakers talk a little bit. They're gonna answer all of these questions. So be
Yeah,
patient.
very, very good questions. I'm loving it.
Yeah, great.
Okay, so we have lots of surprises. So this is like a very famous cartoon which puts together various things that we've learned about what the history of the universe looks like. So some of these I'm not going to talk too much about, but if you're interested, I'm happy to answer. Both Phil and I will be happy to answer questions about it. But basically, cartoon is showing a universe is expanding. So the Big Bang is the story of how our universe began, but it's not the whole story. So we start from when the universe was very small. I'm going to talk a little bit. Well, I'm going to talk much more about the very beginning. But the universe got bigger, and at some point, around 400,000 years, as we discussed, they formed the first atoms, and this is the first afterglow that you see. The afterglow the light of the Big Bang is actually when the first atoms form. But then after that, the universe was kind of dark, nothing was happening, but it was still expanding. And around 400 million years after the Big Bang, um, the first stars form, and then the stars get together, make bigger clusters of stars and galaxies, and um, and then eventually you see we live here around 13.8 billion years after the Big Bang. So we actually know the age of the universe very well. And at the very past few billion years, we know that actually the expansion of the universe has been speeding up. So this is his dark energy that's written here. So this is a brief story of how the universe, based on all our studies, how the history of the universe looks like. But what caused the real mystery, and that's really the heart of our story that we're going to get into, is what caused the Big Bang? What came before this hot, uh, dense plasma that formed the elements? And what happened before it, that's the real mystery. And here I have some words that I put as placeholders here. So inflation is one idea for what happened before the Big Bang at early times. The universe was getting bigger very, very fast. there are quantum fluctuations. These are things, tiny fluctuations that may be eventually responsible for galaxies that we see today, but they started as the small fluctuations at early times. And then there is the biggest question mark of all is this thing is called singularity, which is the very tip of this ice cream cone. What lies at this very tip? What was that? And that's what scientists call singularity. And then the big mystery is what it is.
So there's a bunch of questions again. So, let's see, August, go ahead.
Isn't like the afterglow light pattern called like the microwave background too?
Yes, you're exactly right. We're gonna get to that in a couple of slides. Yes, you're right. Absolutely.
Nora has been waiting. She didn't
Mhm.
raise. Nora, go ahead.
Uh, um, uh, how could quantum fluctuations create the universe if mostly quantum things work on an atomic level, though? How
That's
could it have created the
That's an
universe?
excellent question. And this is the power of this thing called inflation that I mentioned here. So the idea is that quantum fluctuations are subatomic scales, which are tiny, but then something magical happens. When I say magical, it's not really magical. It's based on some ideas in the laws of physics. Is the physics, we don't exactly know how it works, but it's the physical laws that inflation takes these tiny quantum fluctuations and stretches them onto very large cosmic scales, and that becomes our galaxies. So it's like a big magnifier that takes tiny quantum fluctuations and then make them very big.
So the quantum fluctuations just kind of like add up and eventually create the universe?
Yeah, that's kind of what could be happening, but also we need something like inflation for that to happen, right? So you need quantum fluctuations, but on top of that, you need this inflation that stretches them to make them very big.
Okay.
And the change in scale in inflation is absolutely mind-boggling. We're talking about going from subatomic particle size to maybe the size of a grapefruit in a tiny fraction of a second. And you might not think that that's a really big change in scale because, hey, a grapefruit's not that big. But compared to a subatomic particle, it's an unbelievably large change in scale and all happening in a tiny fraction of a second or so, we may suppose.
Yeah, that's the idea.
Yeah, Felix, go ahead. Maybe a couple of more questions. I don't think you guys are gonna pass like the third slide.
Okay.
But yeah, Felix, go ahead. And then maybe move on after that.
What are quantum fluctuations?
What does it mean?
Yeah, very good, very good. So, I'm gonna actually come to this in a little bit, but the main idea is that on very small scales, when we think about things as small particles like electron that goes around an atom, so atom is made out of electrons and nuclei or protons and neutrons. But these small particles, the laws that they kind of follow, they're not very exact. So what it means is that they don't move on a straight path. They're very random. They kind of go up and down, and we cannot exactly pinpoint what they do or where they are. So these are what we call quantum fluctuations. That you may think like a chair or a ball is moving, and you know exactly how fast it's moving or where it's going. But if you actually can zoom in, even for that ball, but especially for smaller particles, there is a lot of uncertainty in what it's doing. And those are known as quantum fluctuations. So there are always tiny particles that are coming and going on very small scales, are there sometimes and then disappear and reappear. These are quantum fluctuations, and we know that on a small scale they should exist. All of the electronics that you use, the computer we're using now, they're using the laws of quantum mechanics. So we know these quantum fluctuations are there because everything that we're using are using these laws.
Okay, I have another question. Is that
Next,
how
okay. Yeah, this is the last one for now. I'm sorry for people who are waiting, but let's just let the speakers move forward a little bit. Maybe we hear
okay?
all of these answers.
I have a comment.
Okay, go ahead.
Okay.
Tell me
The
your comment.
comment is that I've also heard that singularity when I'm learning about about black holes.
Mhm.
That's a
Okay.
very good comment that in fact, indeed, there could be a singularity also inside black holes, and the singularity of the Big Bang and singularity of the black hole are equally mysterious. And in fact, one of the theories, if we ever get to it, is that maybe Big Bang and black hole are the same thing. So they might be the same singularities. So, but let's get to it then. So shall I move on?
Yeah, let's just move forward and
Okay,
then
let's
we
move
answer.
forward, but we can come back to these ideas. Okay, so now how do we know this stuff? Where do these stories about the Big Bang that are some of them are kind of vague, some of them are very specific. Where do they come from? Sorry, it was okay. So scientists use telescopes. Scientists like me, for example, and my friends and colleagues, we use telescopes like time machines because um, light moves with the speed of light. So if you look at things that are far away, you're actually looking back in time. Now, it's a famous telescope you might have heard about, which is NASA's James Webb Space Telescope, or JWST, makes lots of nice pictures like the one you see on the top right. Uh, it actually does look pretty back, very far back, close to the Big Bang. But in fact, the closest to the Big Bang that it gets is like 300 million years after the Big Bang. So the first galaxies that are actually mapped or are imaged by these James Webb Space Telescopes are only like 300 formed maybe, or we are observing them around 300 million years after the Big Bang, or light from them left around 300 million years after the Big Bang. So that's actually not the earliest that we can see. Cosmic microwave background, which one of you guys mentioned, indeed this afterglow of the Big Bang. And that's mapped most recently. I mean, there are many experiments or telescopes that look at cosmic microwave background, but one of the most powerful ones is this Planck Space Telescope that you see a movie of it here. So this is by the European Space Agency. And it actually looks at this cosmic microwave background. So it's a microwave light. It's just kind of like a microwave that you have in your kitchens, but it's not the microwave that's emitted by your microwave in the kitchen. It's a microwave that came from the Big Bang. And this telescope you see is actually imaging the tiny temperature fluctuations of this afterglow or this cosmic microwave background over years, over several years. And this is kind of showing how this happened. The map that you see is basically a map of temperature fluctuations that were present around 400,000 years after the Big Bang. And this is from this Planck satellite. Now, it's not all from the Big Bang. There is a red band that you see is just from our own galaxy. But if you use some methods to get rid of that red band, then what's left is this image, which is basically how the universe looked like 400,000 years after the Big Bang. So that's an image of basically a very, very young universe. Okay, so we can take questions now. Anyone?
Yeah, sure. Let's take some questions. Kai, the same people have same questions. I wonder if other. Kai, go ahead.
How did other elements form if they didn't come from the Big Bang?
Great question. So I think as Phil mentioned, the very massive or very heavy stars, stars much bigger than our sun, when they explode, they could make a lot of elements. In fact, even our sun can make some new elements. But really, most other elements, you need very big stars to explode. And those ones actually make all sorts of elements.
I
you know,
thought stars were only made out of burning gases like hydrogen and helium. How could that be possible?
well, that's kind of what stars do. That if because they are very hot and
Oh,
very
right. They react into heavier and heavier elements, and they soon reach iron,
that's right.
which means it will explode.
Yeah, that's right. That's it. That's how you make supernova explosions. That's very good story, but that's not what I'm going to talk about today. But in fact, you're exactly right about how you make heavier elements.
Dash, do
Okay.
you wanna let me get one more? Dash was waiting from the previous round. Dash,
Okay.
go ahead if
So,
you're still here.
In fact, can I just butt in on
Yeah.
the heavier
yes.
element? Um,
Yeah.
there was a real mystery as to how some of the elements were formed, particularly, I think, was it carbon? And there was a great phrase where God couldn't figure out how to make the carbon, and a scientist called Fred Hoyle figured out how it was done. And the phrase is, and God said, let there be Hoyle," and Hoyle figured it out, and that's how
Right.
we got to
Yeah.
figure out where the carbon came from.
Mm, yeah. No,
Okay, maybe
those are great
one more.
stories. Go ahead.
Yeah, maybe one more. Nora, go ahead. And then Razel.
If space and time doesn't exist, but inside of a singularity, how could a singularity have created space and time?
I think those are excellent questions, and I think it just goes to say that we don't know what a singularity is, so we don't actually have any rules for what can do it, what it cannot do, or whether it actually exists. So what a singularity is kind of like saying that. I mean, imagine I'm sitting here in my room and there's somebody behind that door, but I don't really know who's behind the door. So singularity is kind of where the door is. We know there must be something or there might be something behind it, but we cannot tell because we don't have the right tools and we cannot go and look. And that's what the singularity is. And I think a lot of what I'm going to, well, as much as I can get to it, we can talk about is various speculations about what a singularity could be.
In fact, just one phrase I like is the singularity is not the beginning of the universe, but rather it's the end of our understanding. It's where our current laws of physics break down. And so what scientists like Niyayesh are trying to do is come up with new laws of physics where they don't break down. And that's what our journey is all about.
That's right. And I think we have some notes about the nature of
Yeah,
singularity.
Dash, please don't write on the board. Okay, so let's move on actually, and then
Okay,
yeah,
let's move
we
on.
stop again.
Very good. Thank you. Okay, so what's the big mystery?
I was simply stating that the Big Bang is a poor name for it because there were no particles back then. How is there supposed to be an explosion? There was no
That is
explosion, simply a sudden increase in entropy.
that is a very good point. And a lot of people don't like the name Big Bang. And some people have come up with better names. I think the Big Stretch might be a better name. But unfortunately,
Or the Great Expansion.
that could be a better one as well. Unfortunately, in 1949, the same scientist I mentioned before, Fred Hoyle, he was
The Great
he was like the
Spike in Entropy.
YouTuber. Second,
The Great Spike in Entropy.
Yeah, Dash, let our speakers answer your question, and then you can talk next time. Okay, go ahead.
so Fred Hoyle was this. He was like a YouTuber of his time, like back in 1949. They didn't have YouTube back then, but they had radio shows. And Fred Hoyle was like the equivalent of a popular YouTuber in the 1940s. He had a radio show in Britain, and he had his own idea about what happened all those billions of years ago. And there was this alternative view to his, and so he was describing these two rival theories, and he wanted to come up with a way to express it to the layperson. So he came up with the phrase Big Bang, and the name stuck. And there's a phrase where he said, "Words are like harpoons. Once they go in, they're hard to get out." But the name just stuck.
So I can't tell you why I like the word Big Bang, because I mean, when you think about the bang, like something like this, you make a lot of sound. And in fact, what we see, these fluctuations you see in cosmic microwave background, they are really sound waves. They are just very much stretched across the cosmic scales. Like the sound waves you make, I mean, the wavelength for them is like maybe a few centimeters, but the sound waves that you see in the cosmos, their wavelength is millions, if not billions of light years. And I mean, our Big Bang is actually a bang in the sense that it makes a lot of sound waves, but then the universe expands and the sound waves are stretched. So yeah, it depends on, yeah, maybe it's not an explosion, depending on what you call an explosion, but it is
There
kind
were
of,
no sound waves. How would they be sound waves? There were no particles around.
well, I mean, we see these particles. There are photons emitted. That there was no particle maybe at some point, but eventually there were particles and there were sound waves because we actually measured these sound waves. So what you see, these pressure fluctuations, these blue regions and red regions, they are actually measure of fluctuations of pressure in this primordial plasma. So at some point there were some.
Supernovae.
Okay, so I think maybe we should move on now. But this is a good, I think maybe it's a good point to move on. Shall
Yeah,
we
let's
go to
just
the
move
next?
on. Yes,
Okay.
please. Let's move on.
Okay, so the Big Bang Theory doesn't explain what caused the bang. So where did it come from? What happened before the bang? So why there was a bang? What was before the bang? And here is, I think, one of Phil's movies where he kind of trying to zoom in and kind of see what might be happening if you go earlier on um, to the very origin where there was maybe a point. This could be a singularity, or basically where we don't really know what's happening. Um, but that's kind of where the mystery is. Somewhere how you approach to this point, or even if there is a point there, that's where the mystery
I
is.
should add that animation was made for a film I made with Stephen Hawking. And if you look carefully at that cosmic microwave background, it looks like Stephen Hawking's initials are in there.
Oh yeah, okay, let's go.
Can you
If
go
you
back
see
at
Stephen
all?
Hawking,
Can you
yeah,
see the S and the H?
uh,
You have to look carefully. Yeah, go on. Yeah,
where
she
can
can
you
point it out.
actually?
Zoom
I
in
know.
just a tiny bit more.
Oh yeah, I see SNS.
There it
Maybe
is. Yeah.
I can write. This is S. This is like an S here, and this is an H, right? So Stephen Hawking was a famous physicist who passed away a few years ago. In fact, his office, he used to visit my institute, and his office is next to where my office is now. Uh, but then famously, he thought that his name was in fact in the, well, he said, I think joking, maybe half joking, that his name was on the cosmic microwave background. You could see it like S and H here, right? Cool. I'm gonna get rid of it now. Very good. And I think you have pictures, some pictures of Stephen Hawking and Phil. Um, I think I didn't include it here, but yeah, there are nice pictures of them as well. Okay, so let's see. And then another question, why does the universe have the shape and the laws that it does? So this is actually very important because I mean, we may never know what happened before the Big Bang, but we can actually measure the shape of the universe and the laws of the universe, and we want an explanation. Well, where did this shape come from, and where did these laws come from, and how do they fit together, or do they have anything to do with each other? So these are the big mysteries that are really at the heart of the mystery of the Big Bang. I can maybe just say one more thing and then take questions. So the question of the laws is a very interesting one. In some people say it's the holy grail of theoretical physics, which is the question of quantum gravity.
Okay, guys, if you draw on the board, I have to kick you out of the meeting, so please don't do that. Thank you.
Thank you. So there are these rules. Remember you asked me, and we discussed a little bit about the quantum physics, which is how like small things work, like subatomic particles or atomic particles, like electrons in an atom, or your iPhone, how it works, because it's all based on electronics that use the rules of quantum mechanics. And then you have on larger scales where you have black holes and GPS and gravity, solar system. So those have their own rules. But for some reason, very strangely, the rules of quantum and the rules of gravity don't work together. And in fact, this is, sorry, this is, why is this not moving forward? Oh yeah, this is our friend Einstein, who actually contributed to our understanding, or basically had played a major role in understanding of both quantum mechanics and gravity. But he also realized that these two don't work together. And one of the big mysteries of the Big Bang is, in fact, the mysteries of what rules we should use to understand the Big Bangs, because the rules of quantum and rules of gravity are inconsistent. So understanding Big Bang, in fact, requires understanding how these two sets of rules come together. So I can actually stop here and take questions if before we.
Sounds good.
Mm-hmm. Go ahead.
Yeah, let's go August and then Sid and then Felix. Oh, Razal was waiting also. Yeah, go ahead. Who did I call? Sorry.
So are black holes, so
August.
like, do you think black holes would be like rips or like tears in the universe?
Interesting.
That's a cool cool idea. I mean, in some sense they are. I mean, they basically kind of separate. They if you fall into a black hole, it's almost impossible to get out unless you kind of could very clever somehow use the rules of quantum mechanics. But it's almost impossible to get out. So what's inside of a black hole is kind of like turned away from our universe. So there are all sorts of fun and crazy and speculative ideas about what's inside of black holes. Maybe just the universe ends at the edge of the black hole, uh, or maybe there are other baby universes inside the black holes. One of my friend Leah Smolin, who's one of my colleagues here, thinks that whenever a black hole forms, you make a new universe. So basically, this way you could make many, many universes if you make many, many black holes. So those are it's a cool basically a cool thing to speculate about. But yeah, a tear is one way of describing it, but we don't really know.
One of the exciting things about Lee Smolin's idea is that he thinks that the baby universes would have very slightly different properties from the parent universe. So they might evolve in a similar way that all biological organisms evolve. And in which case you might wonder, one definition of life is something that undergoes Darwinian evolution, in which case you might say that the universe is actually alive.
Mm-hmm. Yeah, that's really cool and mind-bending ideas.
Yeah.
Yeah,
Sid,
good.
go ahead.
Mm-hmm.
Sid.
Another name for the Big Bang is the Great Jump in Entropy.
Okay, very good.
Very good. Yeah. Let me go to Razal. She's been waiting for a very long time. Razal, go ahead.
Is there any evidence to suggest that there might be multiple universes?
Cool. We're gonna get. I think that might be my next slide.
Oh, okay. Very good. Let me go to Sirish.
So I'm not sure if you're going to answer this later in your presentation or not, but how do we actually study these things? So how do we determine, for example, if quantum gravity could work?
Very good question. So, yeah, so there are a lot of these things that would be hard, if not impossible, to study, but we could always kind of try to be clever and look for observational signatures. For example, yeah, we weren't there before the Big Bang or at the time of the Big Bang, but there were these sound waves that I was telling you were made sometime before the Big Bang somehow, and we could actually measure those and measure their properties. So, so that gives us a clue that whatever story we have for the Big Bang or for the singularity or for quantum gravity, we need to get these sound waves with the right properties out of it, with the right shape, with the right color and everything. So that gives us one constraint. And then there are others, and we have to put all of these together and see what are the possibilities that are left. And there are still a lot of possibilities, but we kind of chip away at these possibilities. I can tell you another one, which I'm not going to talk about, but it's something that I work on. I mean, I've been working on for the past 10 years. So this picture of a black hole, you see, if there are quantum things that are happening, like right at the singularity or somewhere at the edge of the black hole, you could imagine sending gravitational waves, which are just kind of ripples in gravity, that get to this quantum edge of the universe and get reflected. Sorry, I'm going to yeah. And then we look for kind of reflection of these gravity waves. And we might be able to detect them because we can actually see measure gravitational waves or gravity waves these days. So those are basically, the more advanced our observations get, the better telescopes we get, the more the different kinds of telescope that we get. We can see gravitational waves, we can see neutrinos now. Then we can try to be clever and think of clever ways of measuring subtle effects of quantum gravity. Some of it may come from the Big Bang, some of it may come from black holes, some of them may come from somewhere else. For example, dark energy that I told you about that causes universe to expansion to accelerate. That could be another subtle clue. And yeah, so the job of a cosmologist and a physicist is to put all these clues together and see what fits best all of these very different, diverse clues on very different scales.
Very nice.
I just want to add one thing. I like to think of it this way. We need quantum gravity to understand the Big Bang, but we also need the Big Bang to understand quantum gravity, because the energy scale of quantum gravity is out of reach of any conceivable particle collider. But the energy of the Big Bang was a giant particle collider. So it could probe quantum gravity. So maybe if we look at the Big Bang in just the right way, we can see signs of quantum gravity. And then when we understand maybe which is the right theory of quantum gravity, we might learn what happened at the Big Bang and even before, possibly.
Very nice. Awesome. Let me call on two people who haven't asked a question yet, Siddharth and then Rex, and then we can move on to the rest of the talk. Because I think you guys have asked questions before, Felix. So just hold on. Siddharth and then Rex. Sorry.
I have a question about black holes.
Go ahead.
Go on.
How come the black hole can pull in light, and how come light can't escape it?
Yeah, that's a great question, and this is one of the predictions of Einstein's theory. This guy's Einstein's theory of general relativity is the theory that he proposed, and it was a successful theory, and it had some mathematical equations. And if you take those mathematical equations and look for all the solutions, people realized pretty early on that one of the solutions is one that actually can pull light in. You just need to put enough matter together on a small enough region. Like, for example, if you take the sun and put it if you could compactify the sun within like 3 kilometer radius, then it actually becomes a black hole. Or if you could take all the mass of Earth and put it within, what is it? Is a few millimeter? No, it's how big was it? Yeah, I think if with a few centimeters, yeah. If you could put it within a few centimeters, then it would become a black hole. It would be a tiny black hole, but you need to kind of make it very, very dense to make it a black hole. So this is one of the predictions of this theory, and it was a very weird and bizarre prediction. It's just something that was part of the theory. Nobody knew that whether that could actually happen in the universe. But now, in the past 50 years, we got so much evidence. Like the most direct one is this picture I'm showing you. And in fact, this picture, Event Horizon Telescope, is one of the main researchers on this is one of my colleagues, Avery Broderick, who is just next door to me at the University of Waterloo. And they managed to actually take a picture of the black hole at the center of the Milky Way, as well as the one that's farther away. So this is the one that was farther away, but they actually have a picture of the black hole at the center of the Milky Way. So universe actually either with very big exploding of stars or maybe other mysterious mechanisms. It manages to make these solutions of Einstein's theory happen in nature through astronomical events. And yeah, that's the way it works. And it's mysterious, but it's predicted by the theory, and it's confirmed by observations. So that must be there.
Okay. Rex, can you wait for the next round? Sorry. Yeah, is it a quick question? You can ask it. Okay. I know you're very disappointed. Go ahead, ask.
It's a bit more of a comment, but I think it's
Okay.
kind of necessary. It's about the black hole universe things. If black holes are kind of like mini universes and will evolve, they can actually also undergo natural selection. If black universes that favor creation of black holes will create more black holes, but universes that don't will eventually, those like lines of black holes will eventually like die off.
You're absolutely right, and that was indeed the prediction of my colleague Leah Smolin. He called it cosmological natural selection, and that you're on the right track. If you were born maybe 40 years ago, you could have beaten Leah Smolin to this idea. Yeah.
Let's move on. I'm sorry for people who have questions, but please wait for the next round. Yes, Niyayesh, please go ahead.
Okay, let's go. So let's go through some of these ideas, and there are a lot of them that we cover. In fact, I forgot, Phil, how many ideas do we cover in the book? Is it 40?
I think it's 24.
24. Okay, 24. I thought it was more than 24. But yeah, okay, that's
Something like that. Yeah.
yeah. So we cover lots of ideas about what happened before the Big Bang and the various models. So I'm just going to mention some of them, the ones that actually Phil has nice animations for. So this is so yeah, there are many ideas about what happened during or before the Big Bang. For example, the inflationary multiverse is one of the more popular ones. So, so the idea is that universe at very early times, or on very large scales in these models, is rapidly expanding and reproducing, and yeah, so and this kind of keeps going on, but there are the small bubbles in these big universe, which or big infinite multiverse, where you could have life and matter and planets. But most of the universe, this inflation is happening, where the basic universe is expanding very fast, and this keeps kind of reproducing and expanding. So this is a picture of this. It's like one of these bubbles, and then you could have many of these bubbles that kind of come to be, each of them like a tiny Big Bang with its own galaxies and stars that come and live and die at some point. But they exist, but there are many billions, or infinitely many of them across the universe. So this is called the multiverse. And in principle, these various bubbles in various places could have various properties. They could have different electron masses. They could have different elements. Some may have life, some may not have life. And yeah, so we, of course, live where we can live, or humans or life can exist only where it can exist. But there could be all of these universes across the entire cosmos, and that's called a multiverse or an inflationary multiverse. So
I
that's
just interrupt with an analogy.
Go ahead.
So my mum makes this fantastic chocolate cake. It's really yummy. And when she puts the cake on the table, we all dive in and take a slice. And then there's about half of the cake left. And then after we've had a slice, we all have another slice. And now there's no cake left. However, if we imagine that the cake more than doubled in size in the time it took us to take between having our first slice and our second slice, then the cake keeps growing every time we have this slice. We can take more and more slices, infinitely many slices, because the cake will grow faster than we can consume our slices of cake. And if space is like that, if it gives birth to bubble universes at a rate faster, it grows far. The bit that hasn't decayed and become these baby universes, if that's growing faster than the rate at which it generates new bubbles, then it would make infinitely many of them.
So that's thanks, Phil. That's a great analogy. And I think someone was asking whether we know these multiverses exist, and it's actually, I mean, we would be living in these models in one of these bubbles, and it would be almost impossible to know whether the others exist. There have been ideas, like another colleague of mine, Matt Johnson, whose office also next door to me, has been has worked on whether if two of these bubbles maybe collide with each other, we could look for the effect of the collision in the cosmic microwave background, which I showed you. Now they looked for it and they didn't find it. So, but it's still a possibility that maybe if you're lucky, we could find signatures of these collisions. But if we don't see anything, that doesn't mean that they don't exist, but also you cannot rule it out or we cannot prove it. So really, it's just kind of a idea or hypothesis. So shall I? Okay, maybe we take a couple of questions and then we go to the next one.
Yeah, if you want to take a question, Akshay, you go. You haven't asked questions yet, and then Connor. We're gonna give chance to other people to talk. Yeah, go ahead, Akshay.
Singularity of a black hole, does that like connect you to a different universe with a separate singularity? That like that does the Big Bang again? Or is it like because like if the singularity can't explode because then it won't be like a black hole anymore because there's no singularity. So is it
Yeah.
just like connected to a different
This
place
is a
or?
good point. It's a very good point. Yeah, so I think this is certainly one of the hypotheses that maybe one of the ideas is maybe you don't really have a singularity, or if you get close to a singularity, you bounce into a different universe. Maybe you don't get a singularity. Maybe you just don't get a black hole at all. So there are actually various ideas. Black holes don't last forever. One of the things that Hawking showed is that even in a standard picture of the black holes, they're not completely black. They have a tiny bit of temperature. So if you wait long enough, they're actually going to evaporate and disappear. So so there are many ideas, and certainly what you mentioned is one possibility. But we don't really know if that's correct, and we haven't been able to either test it or rule it out or rule it in.
Connor, are you still here?
I am not. Well, my question was similar to the other question actually, so I don't think I need to ask the question, I guess.
Okay, thank you.
No worries.
Kai, go ahead. Kai, you've been waiting for a long time. Go ahead.
Well, for dimensions, like 0D is a speck, 2D is a polygon. What connects with our understanding is 10D is the connection of infinity universes.
Sorry, what was the question? I didn't get it. Can you repeat?
Well, it's a comment.
Okay.
Like dimensions sort of come with the universes because some dimensions are are some things of what we're talking about. Like 0D is a speck, 2D is a polygon, 4D is time, and 10D is the connection of infinity universes.
Yeah, so I think I think we could have 10 dimensions, but universe doesn't have to be infinite. But in fact, 10 dimensions is something that's been proposed by a string theory, which is one of the ideas for quantum gravity. In fact, whether there are more dimensions than we see, that's certainly a possibility, but we don't have any evidence for it as of now. Well, that's very good comment. Thanks a lot, Kai.
All right, let's move forward.
Okay, so let's go to another idea. So this is the big bounce cycles. So somehow it could be that the Big Bang was not the beginning, but in fact, universe was bouncing the same way that if you hit a ball at the wall, it may hit the wall and come back. Maybe the universe was collapsing before the Big Bang and then hits singularity or near singularity, and then just changes its mind and decide to expand. And this might keep repeating over and over. So this is one of the great, this is one of the movies that Phil has made on this. So you see, I'm not actually 100% sure,
Oh,
but I
this
think
one
it's,
is the Hartle-Hawking model, actually.
okay.
So here the idea is they replace the singularity with a very smooth surface. Now here we see the bounce.
Okay. Sorry,
In-
I think I mixed. Yeah, I should
Yeah.
have separated them. So forget about this one. Let's skip this one. So because I think we are covering a lot of
Yeah.
models. So let's forget about this one. So this is the big bounce, right?
Yeah.
Yeah.
So here it's not cyclic in this particular case. It could be, but here this is a cyclic one.
This
So
is
the
cyclic.
first one, we might think of it like an hourglass, and there was just one collapsing universe and then one expanding universe, and it forms like an hourglass. Now in this animation, we see it more cyclic, so that it expands and contracts, expands and contracts.
Yeah.
So there are two different visions of the bounce, if you like. One you
Yeah.
might think of like a one-shot bounce, it only happens once.
Mm.
And another idea is that it happens over and over again.
Yeah.
And,
So
and
this
the
is
way I like to think about it is what might reason to think there might be a bounce is if you think of a sponge and you imagine you pour water on the sponge, it will absorb that water. So the sponge is water absorbent. But if you keep pouring more and more water on, eventually the sponge can't accept any more water. So now it becomes water repellent. And so similarly, maybe space is like that. That if you fill it up with more and more stuff, so if you think we wind the clock of our universe's evolution backwards in time, it's getting more and more dense. You're squeezing more and more stuff into it. And the singularity would say it becomes infinitely dense. But maybe it never becomes infinitely dense. Maybe there's an upper limit on the density. And then gravity will switch its properties. So rather than becoming attractive, it becomes repulsive. So then it pushes back out again. And so that would be the rationale for thinking there was a bounce.
Yeah, very good. So thanks, Phil. Are there questions?
Yeah, let's go to Rex and then Felix.
I actually forgot to lower my hand, but that was good timing that you called on me because I started to have a question.
Okay, go ahead.
So this big example of the big bounce theory, when the gravity switches, does it go back to attracting or is it just all repulsing an antiverse?
Good. So the idea is that it's only repulsive when you get to very high densities. So when everything gets very close to together, the densities are much higher than the densities that we see around us today. Then the gravity may become repulsive, and then the bounce happens. But then it would go back to being attractive. And in fact, even there are two different ideas that maybe the direction of time changes. One idea is that time actually moves forward as you go through the bounce. Another idea is that maybe time is actually changes direction, goes backwards. The clocks would tick in the opposite direction when you move through the bounce. But yeah, so let's kind of move on because that would be too many things to talk about.
Yeah, for sure. Yeah, Felix, you go ahead. And then
Okay, I've been waiting a long time. I've heard of the cosmic microwave background, but what about the cosmic neutrino background?
Yeah, that's an excellent question. Now, there is a cosmic neutrino background. It's just neutrinos are these tiny particles that barely interact with anything. We know they exist because we've managed to make them in, say, nuclear bombs or nuclear reactors. But they also, Big Bang makes them, but they are much harder to see than photons. So it must be there. We have indirect evidence for this cosmic neutrino background. And I'm going to show you the evidence for it in a bit. But yeah, we haven't detected it directly because the neutrinos are damn hard to detect, especially the ones that are um, uh, low energy, like the this afterglow of the Big Bang. But yes, this is an excellent question. But unfortunately, it's in fact I just hosted. So Phil knows him. Douglas Scott, who is one of the people in our book, is a good friend. He's visiting me this week in Waterloo, and he just gave a talk about cosmic neutrino background, and he was saying how difficult it is to directly detect it, even though we have very good indirect evidence for the cosmic neutrino background.
So one exciting thing about the cosmic neutrino background, the cosmic microwave background was emitted roughly 400,000 years after the Big Bang. But the cosmic neutrino background would be emitted about 2 seconds after the Big Bang. So it would be really cool to detect it because it would be so much closer to the bang. But as Niyayesh said, it's very, very difficult.
But there is a catch there, that because neutrinos are massive, unlike photons, they actually does not as far. They kind of slow down. And yeah, so we cannot really see very far. But anyway, so there's something cool and then something that's not.
Yes.
But yeah, we
I have
haven't seen.
one more question.
Yes, go ahead.
How do we find evidence for the Big Bounce?
That's a good question. Phil, do you want to take that one?
Yeah, sure. So the cosmic microwave background has all these features in it. So if you see, it has these different colored spots, and they represent different temperature fluctuations. Some bits are slightly colder, slightly warmer than others. And what the people that work on the Big Bounce have done is try to model it and see if there are subtle changes in that temperature map that they predict might be seen for a big bounce. So it's very subtle, and there are certain correlations, and so that's what they're trying to do, to try and work out what should the temperatures look like given a bounce rather than no bounce. And there are different models of the bounce. So remember we talked about that thing called inflation. So that was this very rapid growth. So some versions of the bounce would have a bounce and then inflation. Other versions would get rid of inflation altogether and say there wasn't any inflation. So that would have different properties, particularly for what are called gravitational waves. So these are like ripples in the whole fabric of space and time. And the version of the bounce that doesn't have inflation would make different predictions about those gravitational waves than the ones with.
I see. By the way, I just know something very funny. A question, when anybody asks a question, it just leads to more questions.
Yeah, exactly. Felix, let other people talk.
That's
So
like
I just want to, sorry, yes.
eternal inflation. That's how it works.
Yeah, exactly.
Yeah.
I just want to point out that it's like it's been an hour. I don't know if you guys want to we want to respect your time. I know there's tons of questions and people want to really move forward. It's up to you if you want to take questions or move forward. It's up to our speakers. Do you want to give them a little bit more or
I'm
answer
happy
questions?
to go on. It's really up to you guys.
Okay.
Yeah, I think people want to hear, like they would never let you go. So this is like we want to respect your time also.
So
Do you want
go
to
ahead.
just talk or you want to answer questions? Because these guys are full of answers. Do you want to have?
Yeah, let's see. So I think I have two more movies
Okay,
because
yeah,
I
let's
think
watch those.
so. Phil is a real magician with all these movies. So
It's
I
amazing.
think I would like to see those. Well, show
Yeah,
those.
yeah,
And
let's do that.
then afterwards, maybe we could just go into questions. So
Okay,
Big
awesome.
Bounce, we talk about it. So you could be one shot or cycles, but there are other possibilities. So this is one of my favorites because this is a model that we came up with about 10 years ago. And then Phil went away and worked with others to make this amazing movie of it. So basically this idea is that the universe, the Big Bang was actually a black hole or was born out of a black hole. So you see in this case there's an exploding a star in higher dimensions, and it makes a black hole, but the idea is that this is in 4 dimensions instead of in 3 dimension. and there is a black hole that sits there, and
Oh, we
suddenly,
should take on I should say 4
yes,
space dimensions.
yes, for a space dimension. Sorry, yeah. So there is one extra dimension of a space in this case, in this universe. And again, so I'm just going to go back here. It forms a black hole in this, and then the surface of this black hole suddenly there's an explosion out of this. Our universe comes out, and then this is in fact it's supposed to be our universe. This is where cosmic microwave background and galaxies eventually form. But yeah, so here the idea is that in fact we come out of the horizon of a black hole. And yeah, so this is another model, and it has its own set of predictions. And I'm going to show you the last movie, which is I think the most recent one, I think. And
Yeah.
this one is if it is a time loop, which when we talk about these cycles, but what if universe just goes back on itself, so everything keeps repeating exactly the same way? So the entire universe is a time loop. So let's look at this one. So this is, we call it periodic time cosmology, but you start, universe starts like this, like a fractal, and expands, and then you have the cosmic microwave background, and then you have the galaxies, and at some point in the galaxy's finished, the universe expands and becomes infinitely big, and then out of the middle of it, the universe is born again, and the time goes on a loop, which is very bizarre. But again, this is something that with mathematical models, we could actually make them fit. And yeah, so the universe everything goes back on itself in this time loop. So I think I'm just going to say, before getting to the question, the main thing, now these all sound like speculations, but the idea is that we have a lot of data that our models have to fit. And this is an example of the data, which is kind of the gold standard of the data, the fluctuations in temperature of the cosmic microwave background as a function of angular scale. And we have very precise theories with these lines, and then very precise data that we have to fit. That is why most models, if you just come up with a model, is probably wrong. So you have to work hard for your model of the Big Bang to fit the data. And then this is kind of one of the set of the data you have to fit, and then there are other kinds of data. So we have to kind of combine math and observations and creativity to come up with models that are interesting, but at the same time also are consistent with data. But sometimes we disagree, and that's a good thing. Sometimes there are fights. These are two of my friends, like Paul Steinhardt and Alan Guth. They both were pioneers in inflation, but nowadays they are very they disagree a lot with each other. Paul Steinhardt is against inflation. Alan Guth is still for inflation. There are papers against each other, petitions, and there are lots of interesting back and forth, which you could read about in our book if you're interested. And so every new discovery, though, the more observations we have, it brings us closer to understanding where we come from. So that's it. Sorry, you were going to say something, Phil?
Yeah, there's
sorry.
a phrase from the scientist called Richard Feynman,
Mhm.
who has a small part. If you saw the movie Oppenheimer, or if you get to see that movie, there's a guy playing the bongo drums. He's a very famous scientist. And he said science is speculation in a straitjacket. So the straitjacket is that data that you see in that chart. So you can come up with speculative ideas, but they are constrained by that data that you have to fit. And so it's not quite the Wild West, although to some degree it is, but not to like, it's constrained speculation. So there are degrees of speculation.
Very nice. I think
Very
Jonah
good.
A had a question. Oh, are you ready to answer questions? Sorry.
Yeah, absolutely. I think that's it. That's all I
Okay,
have.
awesome. Very good. Jonah A, do you want to say your question?
Sure. So back to the Big Bounce theory. How does the Big Bounce theory explain the universe shrinking before the bounce, and will it shrink again at some point? If so, then why?
That's a good question. So one of the problems in cosmology is that you could always ask what happens before what and what happens. So basically, you always can ask question. Okay, so but what happened before that, and what happened before that, and what? So it's almost impossible to kind of answer that unless everything happens in a loop. So that is why I like my time loop universe, where then there is there is no point in asking what happens before that because everything happens in a loop. But indeed, this is a question that why universe was contracting before the big bounce, and what came before that, and what came before that. So again, those are more and more speculative questions that we could give speculative answers for, but those are not necessarily good or right answers, but they're just possibilities. So yeah, this is the nature of cosmology or astronomy, that there are some questions that we don't know the answers to, but it's a good thing to ask them. Maybe in 100 years we get to know the answer. Like 100 years ago, we had no idea, or maybe 200 years ago, had no idea what was happening at the centers of the stars. But now, 100 years ago, we learned that it was nuclear reactions or fusion that was fueling the stars. So as our understanding develops and our observations get better, we can push the boundary farther and farther back in time and farther in space, but there will always be questions that are left, and that's the nature of science.
I have a question about the loop. The
Yes.
picture that you showed shows a sudden collapse at the end.
Yeah.
How's that possible? Like, what is happening there?
Yeah, so it's a cool thing. So this actually based on an idea that Roger Penrose, who is a very famous physicist, had. So he in fact won the Nobel Prize about a few years ago for predicting that black holes exist, and basically there is no way of getting rid of black holes in a theory of relativity. But one of the recent ideas is that basically maybe in the very far past or in the very early times, universe kind of forgets about the scale. So this looks like a very big universe and looks like a very small universe. But the proposal is that in these extremes, very early times or very late times, universe becomes a scale invariant theory, or the theory of universe is so-called conformal. His idea is called conformal cyclic cosmology. And then basically, because a scale doesn't make any sense, you could match a very big scale to a very small scale. So he calls it conformal rescaling. But basically what it is that, yes, this is a big universe, but this is a small universe. But in fact, these are equivalent to each other because you cannot, the theory becomes a scale free. So it's this rule which it's a bit strange, but it kind of makes sense. In a sense, one way of thinking about it is that imagine you have, say, two things that, I mean, if we know rotation is a symmetry, so I can kind of rotate this hand and then kind of match them together because I know, I mean, everything is the same. I can kind of turn this. So you want to do the same thing, but instead of rotation, you want to do it with rescaling. And then you kind of match a very big universe to a very small universe. And yeah, the rules of the physics as we know it right now, they don't allow that because the big and the small are very different. But the idea is that at these early times and late times, this becomes a symmetry, and then that could allow actually to match a very big universe and a small universe.
I think one way to think of it, maybe see if you like this one, Niyayesh, is that in order to have a scale, you need to be able to build a ruler or a clock. And if the universe is in such extreme conditions that it's not possible to build a ruler or a clock, then you don't have any scale. So that's kind of what is proposed is happening at the sort of very early universe and the very late universe.
Yep, yeah, that's right. Yeah.
Okay, that's very good. But this becomes kind of similar to that kind of your bubbles growing and shrinking in that sense, right? Like it's if that's the same scale as this, then it's kind of very similar to
I
the other
think
theory.
so. This is again, since this is our own proposal with my student, I can be more specific here. So the difference is here because there is just one history. Everything in exact detail should repeat. So it's not just the,
I see.
I mean, just the overall
Oh, I see.
properties
Okay.
are the same. The same galaxies, the same structures
Oh, okay.
would actually repeat. Yeah, and in
Oh,
fact,
I
it's
see.
kind of interesting how you could match like all the structures to new structures. Everything should exist basically so basically universe models are a fractal. So this is kind of what you see that under rescaling it should kind of map to itself. And yeah, that's the difference is that in the other cycles, the different cycles have nothing to do with each other. You could have different galaxies with different stories and I don't know, different people, different civilizations. But here, everything is the same thing.
Okay. Yeah, sounds good. We have Rian who never asked a question. So we give one to Rian. And then maybe other people can. Go ahead.
I have a question on the one about how universes are born from black holes.
Yes.
So if the outer universes have like one more dimension than the inner ones, so would that mean like as you went further out you'd encounter like fifth and sixth and seventh spatial dimensions?
Well, so that requires being able to get out. So in these models, and these are actually called brain world models, you're kind of stuck on some surface. It's kind of like an ant who kind of lives or moves on some say, piece of paper. So it might be able to see outside, but they cannot get outside of the piece of paper. They're kind of stuck under piece of paper. But now imagine even if the light couldn't get out, light was also stuck onto that piece of paper, the ants would kind of stuck on 2 dimensions, wouldn't know about these things. And that's kind of the idea that in these models, we are stuck to this surface, which is our 3-dimensional space. The 4th dimension, the light cannot get there, and we cannot get out. Now, gravity can get out, so there's some gravitational effect we might be able to see. And yeah, so it could be some ways of learning about these extra dimensions, but yeah, so in these models, you have to work hard either to go to very high energies or very large scales to learn about these extra dimensions. Otherwise, we're kind of stuck to our own dimension. We don't know, we cannot easily probe what's outside.
And so and based off of the same theory, like a black hole in our universe could lead to like a 2-dimensional universe?
It's possible. Yeah, it's not exactly the same theory because like 3 dimensions and 2 dimensions, like things are different in them. For example, you don't have in 2 dimensions there is no gravity. um, so so like a lot of things are very special about 3 dimensions that we live in, and in 4 dimensions they work differently, and in 2 dimensions they work differently as well. So yeah, so maybe, but yeah, it's not that just everything that works in one dimension should work in other dimensions. Yeah, so the dimension actually changing it makes a lot of differences.
I see. Okay, Sirish, you go. August, Nora, and Kai in that order. Sirish, go.
So in the actual field, when you're working on models like these, how are these models developed? So if you have some base observations, how do you
Yeah.
come up with these ideas and formalize them?
It's an excellent question, and I think everyone has their own process, and I don't think necessarily any of them is right. The thing is that we have these straitjackets, what Phil was talking about, that we want a theory which can make predictions. So you want some curve to come out of this theory, and you want it to be, so first of all, you want to be able to make a prediction, and second, you want this prediction to be consistent with observations. But how you come up with this theory, it's really up to you. And in practice, what really happens is people kind of keep combining things we already know about. For example, we know about black holes, we know about dimensions, so maybe we could change them. So kind of they change things that we know about a little bit, or we could borrow things from elsewhere and see whether they could be used here. And yeah, I mean, a lot of the things that you hear, these are things that we've seen elsewhere in some other context. And make bounce is something that we see in everyday life. Whenever say you throw a ball at the wall, it bounces back. And you wonder, okay, so maybe something like that could happen for the universe. Or the loops, we do see them, not in time, but maybe we say if we see loops in a space, can there be loops in time? So we kind of wonder about these things. We borrow ideas from one place, change them a little bit and see whether we can adopt them. But ultimately, the thing is that can we come up with predictions out of them? Because otherwise, these are just stories or fairy tales. And the difference between our stories and the stories that you may read in kind of fiction books is that we come up with math from our stories, and that's what makes these stories different.
I just add that I'm not a scientist, but what I do is interview the scientists that work in this field. So all these people that you see here. So I asked them to tell me how they came up with these ideas, and maybe I could give one or two examples.
Sure.
So here in this picture you see Alan Guth, and what he came up with this idea called inflation, which is a very rapid expansion of space, and it's a theory that people think leads to a multiverse. So what happened was, in the 1970s, it was thought that the theories that they had at the time would lead to some new particle that had never been seen, and it should flood the universe. And obviously, people looked out into space and they never saw these particles. So they thought, we've got to change, we've got to do something to account for that. Where did all these, why don't we see all these particles that it looks like our theory predicts? So they came up with this idea that maybe if the universe cooled in a certain way, some kind of novel way, which actually you can do as an experiment at home. If you get really pure water and you put it in the freezer, actually it can stay as a liquid. It's really weird, but it has to be very pure water. Then when you take it out, and if you shake it, it will suddenly become ice. But this idea that it could stay as a liquid, even when it's below its cooling point, is called supercooling. So they imagined that the universe, what they thought, well, could this affect why we don't see all these strange particles? And they thought, yes, this would actually prevent all these strange particles from forming. So they were like, we're onto something. And then there were actually two people working on this, a guy called Henry Tai. Henry Tai went off to China because that's where his family were. They were in Hong Kong. So it was Christmas time, and something was sort of nagging on his mind. And he said, I wonder this cooling effect that we were looking at, would it change the rate of expansion? Alan, can you work on this whilst I go off to China and see my family? So Alan Guth worked on this, and he calculated, oh my God, it would lead to this fantastic growth spurt. And then there were these other problems in cosmology that Alan had learnt about, and what he realized was this growth spurt would solve those other problems. So then he got really excited, and so he thought, okay, this is a great idea, and we should pursue this. And so that was how the inflationary cosmology, and it's led to this idea of a multiverse, came about. And then maybe give one other example, this idea of a bounce. So what happened in that case? I mean, there have been many versions of it. I'll just give one. So people had developed theories of quantum gravity where we're trying to mix the physics of the very big and the physics of the very small. So they came up with these theories of quantum gravity. One is called string theory, one is called loop quantum gravity. And in some of these versions of these theories, they calculated that actually the density of the universe, how much you could pack into a certain volume of space, would have an upper limit. So in the singularity, remember we saw that as our first slide, it goes to infinity. But they were suggesting, no, actually, if we go to quantum gravity, it would have an upper limit. And when you reach that upper limit, you would bounce out again. So remember with the analogy of the sponge. So what they were trying to do is run simulations of the universe going backwards in time, but then adding in these new quantum gravity corrections. And then they saw when they ran their simulations that it bounced back out. So that was how two of these ideas came about.
Yeah, very nice. Thank you so much. Yeah, August. We take two more questions and then we can wrap it up. Yeah, August, Nora, and Sid. Sorry, go ahead, August.
So
No.
after all, we are all just a bunch of molecules well, they're all theories, and after all, we're just a bunch of molecules compelled to find answers.
Mm-hmm.
Yeah.
That's
All
right.
Very nice. Nora, go ahead.
So back to the big bounce. So I've read that white dwarfs are really, really dense.
Mm-hmm.
So I'm wondering, could white dwarfs form many universes?
This is a good question. Yeah, so white dwarfs are dense, but they're not quite dense enough to reach these scales where quantum gravity would happen. So you need to form for these models, you need to form a black holes to kind of make another universe, if that works. And white
Wait.
dwarfs are still too big to become a black hole.
So is the big bounce theory the same as the black hole theory, basically?
They could be related. In fact, our friend, our joint friend Carlo Rovelli and Francesco Vidotto had proposed to call them Planck stars, where when you form a black hole, at the center of it, you kind of, the singularity of the black hole bounces out, and then you eventually get like a white hole, which is like a reverse of a black hole. So black hole is everything falls into it. White hole is everything falls out. So kind of an explosion. And yeah, it could be if you have a big bounce in the center of a black hole, then you can get like an explosion, or which is like an inverse of a black hole. That's a possibility. But also it may be that these are different things, that maybe the black holes remain black holes. But in the universe, when you the Big Bang, instead you replace it with a big bounce, because at the end of the day, they're not. I mean, there's a lot of similarities, but there are also differences. Like a universe is very uniform on larger scales, but black holes are very messy. So it's not clear that they have to be the same thing. So yeah, so I think it's certainly possible, but it also is possible that they're different.
Sid, did you change your mind? You don't have any question anymore?
Yes.
Okay, that's fine. Sirish, go ahead.
So if I were to go about, for example, astrophysics, this kind of research as a career, so how would what would you suggest for going down that path?
Very good. So basically, you want to do your degree in either physics and astronomy, or physics or astronomy, or it could be physics and astronomy. You do an undergraduate degree. You could also do it in like some engineering degrees, but it would be harder to switch in graduate school. So then you want to do a graduate degree in again either physics or astronomy or astrophysics. And that's basically where you learn how to do research in this topic. And of course, Big Bang is only one of the topics you could work on. You could work on exoplanets. You could work on black holes. You could work on gravitational waves. You could work on um, other topics like clusters of galaxies or galaxy formation. And that's only in astronomy. And there is quantum gravity, there is particle physics. There are lots of areas where there is active research or cutting edge research that's happening. And then if you do a PhD in one of these topics, then you basically become a researcher. And at that point, you kind of continue working, and then so the next step after you get a doctorate or become a doctor in this any of these areas is you kind of can continue becoming a researcher. Usually there are kind of some temporary jobs that you could apply for. They're known as postdocs. Uh, and people usually do them for, I don't know, 3 to 6 years, sometimes longer, sometimes shorter. And after that, you could apply, or during this time, you can apply for faculty positions. And then if you're successful, then you would become a professor. There are other possibilities. You could become a researcher in, say, national labs. So, for example, Fermilab, or Brookhaven, and there are other national labs where they actually hire cosmologists. And also, of course, at any point, if you decide that you don't want to keep doing research on any of these topics, you could switch your field, or you could even kind of go to another area. Don't stay in academia, basically. That's another career route. So there are many career routes that exist. They are competitive, many of these. So you should kind of work hard, and then so not everyone can get necessarily become a professor or a researcher, but that's kind of what you go through. Okay.
Right. Thank you so much. Yeah, so maybe this is a good time to stop. But I want to thank you both to be here, and that was great. And the students had a lot of fun, and they had a lot of questions. Let's just thank our speakers. We can't clap for you, but just a
Thank you very much.
very short
Thank you.
clapping.
Thank you.
Yeah, thank you so much, and thanks for staying so late, kids. I
Yeah,
know a
no
lot of
problem. Thanks for excellent questions. It was really fun.
Yeah, it's already like 1 o'clock in London.
That's right.
it must
Ah,
be. Yeah,
that's
Yeah,
great.
I should
it's
get to
very
bed.
late for you. Yeah,
Okay.
thank you so much, especially for
It's
that.
1:32. It's pretty late. The longest time I stayed up is to 12:06.
Oh, okay. So you
Okay.
I
should go
stayed
to bed
up
soon.
all night before. I also really enjoyed this, so
Thank you
Thank
so
you
much.
thank
very
you.
much.
Thanks to
Bye.
all of you. I
Thank
really
Thank you.
enjoyed
Thank
it.
you.
Thank you so much.
you.
This was